The example I mentioned in class related to the direction field, I'm going to refer to my lecture notes and then show you an example what we need to do to create a direction field from scratch. And then the idea, precisely mathematical idea about the direction field. So we'll start off with definition, formal definition, and then an image of a direction field. And then we'll transition into the process of building one from scratch. The most typical examples that you see are examples where the direction field is given already, so it is created, and then a variety of equations is provided, and then you're trying to match the direction field with a given equation by simply selecting points in the system of coordinates, identify the coordinates, and plug them in. And once you plug them in, you are going to see clearly if they do satisfy the given equation, and then the direction field is going to match with that particular equation. Now, the example I selected is more focused on allowing you to understand what the direction field is all about. So when you build one from scratch, of course, without using any support for any technology, then you get a better understanding. So let me start off by sharing. I'm going to share screen and then go directly to our site. This is our Brightspace site. So you go to content, couple of things on the left hand side of the content option. Under the table of content, you're going to the lecture notes. And this is where the document is posted, direction field example. Now, I'm currently working on with the update of the lecture notes for dated as 4 and 6. So these are upcoming lecture notes. And then I did finalize the detailed solution of practice quiz. So you notice that practice quiz number 1 is posted available in there, but not the solutions. You will see on Tuesday during the class time, I will go over the solutions, and then at some point Tuesday, the solutions will be posted. Even though you got the copy of the practice quiz, the reason why I make that possible and then available to students almost like 10 days before the official day that you're taking the quiz, to allow you sometimes to do the work on you. Now let's get to the example. So idea behind it, create a direction field for the differential equation. I'm using a specific differential equation y prime, which is the first order derivative of variable y with respect to x dy dx, equals to x squared minus y squared. Use this differential equation to sketch a solution curve passing through the point -1 and 2. So use x and y values ranging from -5 to 5. Now, what is a direction field? Before I get into the details, the way I proceed building up from scratch a direction field, I'm going to go to the image of it, and then I'll come back to this image while I'm working to generate the direction field. So it's a collection of line segments. Line segments are defined to be part of individual points in the system of coordinates. So you see points on each of the quadrants. And these line segments are defined based on the point that you're selecting in the system of coordinate and the slope of the line. A line has no boundaries, but a line segment has 2 endpoints. So the direction field requires line segments. So in other words, you are going to sketch the graph of the line at the given point that you identify, but then you only need 1 unit line segment for that specific direction at that point, not the entire line. And you repeat this for any point in the system of coordinates to create the direction field. So a collection of all these line segments define what is known as the direction field of the differential equation. Now you mind up thinking why we don't call this a collection of line segments or lines or a set of lines, because these lines that we are generating, their slopes is based on a differential equation. Why? What we know about the slope? We know that the slope, I'm going back to calculus, the slope is the rate of change of y with respect to x. And the rate of change, as we all know, the given function. So to determine the slope, you use the first order derivative. So in other words, the slope, if I go back to calculus, is computed, a slope of the tangent line is computed by using the first order derivative at the given point. So now you're learning another component of the direction field. So these are not just lines in general or any line. These are tangent lines at the given point. So precisely, a collection of line segments that belong to the tangent lines. Tangent lines are defined by a first order differential equation. So now let's start off with our equations. This y prime is dy over dx. Now the other thing that is important, you need to provide the domain and then the range. So we're not doing this in a position that we are using all real numbers for the domain and range. We have to be specific for the direction field that we are providing or creating from scratch. So we are only allowing x's from -5 to 5, and we are only allowing y's from -5 to 5. So it's a bounded space. Now, the way I start, I focus on the given equation, and then the first thing in mind is defining a spatial slope. There are two scenarios of the slope of the line that are in the category of spatial. One of them is the scenario of no slope. These are vertical lines. That's not what we are looking for. We need this to be well defined, because no slope means undefined. So we need the direction field to be well defined. And the other spatial scenario is slope equals to 0. And we are aware that slope equals to 0 makes the first order derivative equals to 0. So we're looking at the special case where y prime, which is the first order derivative, is 0. If this is 0, then the left-hand side becomes 0, the right-hand side is set equals to 0. So that generates an equation, x squared equals y squared. And then we isolate x by taking the square root of both sides. So square root of x squared is x, and square root of y squared is plus and minus y. Now, these two equations, so x equals y and x equals -y, generate two lines. These are known as the bisectors. X equals y is the line connecting the bisector of the first quadrant and the third. When I say x and y, these are all points of the form x1, y1, x2, y2, x3, y3, x4, y4, or x -1, y -1, x -2, y -2, x -3, y -3, x -4, y -4. At every single point now, one unit, the length of it, I'm going to draw a line at the top of the point that is going to be part of the collection of lines that create the direction field. And then this line that I'm creating has a direction that is defined by slope being 0, which means that the line is horizontal. So this is a collection of horizontal lines that you set through the bisector of the first and the third quadrant, and the collection of horizontal lines at every single point, line segments that are horizontal at point 1, 1, 2, 2, 3, 3, 4, 4. Same thing in the third quadrant, -1, -1, -2, -2. And then in the second and the fourth, the bisector and of the second and the fourth is a line that goes through the point where x equals the opposite of y. So let's say if x is +1, we're expecting the y to be the opposite, -1. So these are point 1, -1, 2, -2, 3, -3, 4, -4, or x equals -1, y is 1, x equals -2, y equals 2, x equals -3, y equals 3, x equals -4, y equals 4. So these are all points that we use to draw horizontal lines of line segments of one unit that represents the collection that we are looking for. So that pretty much takes care of special cases of the slope. Now, the other cases are cases where the slope is positive and the slope is negative. That's going to depend on what you are selecting. So now in the range for all the x's from -5 to 5 and the y's from -5 to 5, you have to pick now any point. So I'm going to select a point just to give you an example. Let's say the point that I'm looking for is -1 and 2, because it is asking the direction field passing through, so the tangent line of the curve that is passing at -1 and 2. So x is -1 and y is 2. So if x equals a -1 and then y is 2, then you are going to plug them in. So now I did kind of like, to make it easier for you, I did like kind of like a little table. x1, y1, x1, y2, x2, y3. So let's say I took those values, so I got a point. So let me go back to the graph. I focused at this point right there, x equals 1 and then y equals 2. And then I go to the equation. The equation is y prime equals x squared minus y squared. And then I plug in. My goal is to get y prime, by the way. If you're wondering how in the world you're going to plug in y prime, I'm not plugging in y prime. I'm plugging in x and y. Y prime is what I'm finding. Y prime, which is the derivative of y with respect to x, once you plug in the coordinates of x and y, becomes slope of the line, tangent line. That's calculus 1. So I plugged in x1, I got 1 squared minus 2 squared, so that's -3. So that means y prime now becomes a slope. So slope is -3, which I write it as, because slope is rise over run. So it's -3 over 1. So that means I have to go down 3 and over the 1. And that's what I do. If I have to draw the entire line, this is the point that I'm starting. So that particular point, how come the point has this direction? Because I have to go down 3, 1, 2, 3, and over 1. And then I simply connect. I don't draw the entire line. At the given point 1 and 2, I just draw the line segment that is part of it. And then I continue like this. So the next point is a table 2 and 3. So I get a -5. So -5 over 1. That means 5 units below or down 1 over. So this is x2 and then y3. So at this point, I go 1, 2, 3, 4, 5, and then 1 over. And then if you notice, the direction of this line is pretty much what I'm connecting in there. I only draw a line segment of 1 unit at top of the point 2 and 3. And you can go back to this point now, -1 and 2. This is going to come out the same as our point, the same slope, but this will be plotted in a different point. So what I showed you is point 1 and 2. This is going to be on the other side. So this is -1 and 2. So -1 and 2, you're going to draw the line segment that has a slope -3 over 1. So 3 units down, 1 over. So from this point right there, you're going to go 1, 2, 3 down, 1 over, and then you're going to connect. And it's a good practice. So feel free to practice on your own. Okay, best of luck. Bye-bye.